Learn like a pro.
Okay, here's a wild thought for you. The soft, gray stuff inside the pencil you write with, it's made of the exact same element as the hardest, most brilliant diamond on the planet. I mean, how is that even possible? It's one of the coolest puzzles in chemistry, and you know what? The answer is actually pretty simple and kind of elegant.
So on one hand, you've got diamond. We're talking about the hardest natural substance known to man. It's dazzling, it's clear, and it can literally cut through steel. And on the other hand, you've got graphite, the soft, dark material in your pencil that flakes off onto paper with just the slightest pressure. Total opposites, right?
So, that's the big question. How can these two materials be so completely different if they're both made of nothing but pure carbon atoms? Well, the secret, the entire secret, lies in how those atoms are connected to each other. And that is exactly what we are going to unlock today.
To crack this carbon code, we first need to get a handle on how atoms connect in the first place. And it all boils down to a really powerful idea that we can think of as atomic handshakes. Now, this atomic handshake has a proper scientific name, a covalent bond. It's what happens when two atoms get together and decide to share a pair of their electrons. See, neither one wants to give an electron away, so they compromise, they share. And this sharing creates this incredibly strong connection that just locks the two atoms together.
Let's actually watch this happen with two fluorine atoms. So you can see each atom starts out with 7 electrons in its outer shell, but it really wants to have 8 to feel stable. So what do? Simple. They each put 1 electron into the middle and share it. That shared pair, right there, that's our strong covalent bond. That's the handshake. And the other electrons that aren't part of the handshake, we just call those lone pairs.
And just like in real life, these atomic handshakes have different strengths. A single bond, that's when atoms share just 1 pair of electrons. A double bond is kind of like a two-handed handshake. They're sharing 2 pairs. And a triple bond, well, that's the strongest of all, where they're sharing 3 full pairs of electrons. Super strong.
Okay, so we know atoms form these strong handshake bonds. But the next piece of the puzzle, and honestly, this is the most important part, is how they organize themselves. Do they form tiny, separate little teams, or do they build massive, continuous networks?
And this one difference, it changes everything. Over on the left, you've got these small crews, or simple molecules. Think of water. The covalent bonds holding each little H2O molecule together are super strong, but the forces between one water molecule and the next are really weak. Now look to the right. Those are the giant networks. There are no separate crews here. It's just one huge, unbroken web of strong atomic handshakes going on and on forever.
So what does this mean for how they behave? Well, for the small crews, because those forces between the molecules are so weak, it takes almost no energy to pull them apart. And that's exactly why these substances have low melting and boiling points. It's also why they often evaporate so easily. And since all their electrons are tied up in bonds inside each tiny molecule, there's nothing free to move around, so they don't conduct electricity.
And this right here is probably the biggest takeaway of this whole thing. When you melt or boil something like water, you are not breaking the strong covalent bonds inside the molecules. All you're doing is overcoming those super weak forces between them. That's the key.
Okay, we've got all the clues we need. We know about atomic handshakes, and we know about small crews versus giant networks. So let's go solve our carbon mystery. Diamond versus graphite.
So here's diamond's big secret. It's a giant network. Every single carbon atom forms 4 incredibly strong handshakes with 4 other carbon atoms. What you get is this perfect, rigid, 3-dimensional structure. It's like an unbreakable atomic jungle gym. To actually break a diamond, you'd have to snap billions of these super strong bonds, which is why it's ridiculously hard and has a crazy high melting point. And since every single electron is locked into a bond, none are free to move. That means no electrical conductivity.
Now, let's check out graphite. The structure could not be more different. Here, each carbon atom only makes 3 strong bonds. This forms these flat hexagonal sheets, kind of like atomic chicken wire. Now, the bonds inside each sheet are still very strong, but the forces between the sheets, super weak. It's like a stack of paper. This lets the layers slide right over each other, and that's what makes graphite so soft and slippery. Oh, and remember that 4th electron from each carbon that wasn't used in a bond? It's free to just wander around between the layers. And this sea of moving electrons is exactly why graphite can conduct electricity.
And you know, this whole giant network idea isn't just for carbon. Take a look at silicon dioxide. You probably know it better as sand. It has a very similar 3D lattice structure to diamond, with strong bonds holding everything together in a rigid grid. And that's why sand has such a ridiculously high melting point.
So, there you have it. The mystery is solved. It all just comes down to the atomic arrangement. So let's pull everything together and look at one final head-to-head comparison.
This chart just lays it all out perfectly. Look at the structure row. We go from small molecules for water to a giant 3D network for diamond to giant 2D layers for graphite. And that structure directly causes the bonding type below it. And that bonding explains all the properties. Low melting point for water, super hard for diamond, soft and slippery for graphite. And look at that last row. Only graphite has those free electrons, so it's the only one that conducts electricity. It's a straight line from structure to property. Amazing!
And this powerful idea that structure determines property, it applies to everything. I mean, think about polymers, the long molecules that make up plastics. They are giant molecules, for sure, but they form these long, kind of flexible chains. The bonds inside the chains are strong, but the forces holding all the tangled chains together are weak, and that's exactly what gives many plastics their unique flexible properties.
Okay, that was a lot, I know. So let's wrap this up and really lock in the most important ideas from our little dive into carbon's secrets. If you only remember 3 things from today, please make it these 3 golden rules. Number 1, diamond is so hard because every single atom is locked into one giant, strong 3D grid. Number 2, graphite is soft because it's made of strong layers that can easily slide past each other. And number 3, graphite conducts electricity. Why? Because it has those free-moving electrons between its layers. Simple as that.
All right, you ready? Time for a quick, rapid-fire review. First question. When you melt something simple like ice, what forces are you actually breaking? Are they the strong covalent bonds or the weak forces between the molecules? It's the weak forces between the molecules. You got it.
Question 2. Why is it that graphite can conduct electricity, but diamond is an insulator? What's the one key difference? It's all about those free-moving electrons that graphite has. Diamond keeps its electrons on a tight leash. And for the last one, in the structure of diamond, how many atomic handshakes or covalent bonds does each carbon atom make? It makes 4. That's what builds that perfect super strong 3D grid.
So when you get right down to it, it's all about the arrangement. The very same building blocks, just simple carbon atoms, can create the soft stuff in your pencil or the hardest gem on Earth. It really makes you wonder, right? Now that we understand these rules of how to build things atom by atom, what incredible materials are we going to design next? The possibilities, they're pretty much endless.